So, in the last few weeks, we have seen how we can design and use the various features available in the Verilog language, and through a number of examples we saw how we can model both combinational and sequential circuits. Towards the end, we have seen how we can design efficient digital circuits, say using the concept of pipelining, let us say. So, we saw that if we use pipelining, then without investing more in terms of hardware, we can gain a significant speed up. Now, we shall be looking at a much more complex example, namely that of designing a complete processor. See, when I talk about a processor, I talk about something called an instruction set architecture. So, when you are using a processor or programming a processor, you have some internal registers and you have an instruction set, and using those instructions belonging to the instruction set, you can write a program to solve any problem. This is the idea. So, in this lecture we shall be starting our discussion on the design of a processor in Verilog with and utilizing the concept of pipelining. And the kind of processor that we look at is something called reduced instruction set architecture or reduced instruction set computer, RISC in short, RISC, which is rather easy to implement in hardware and in particular in a pipeline. Okay. So, the topic of our discussion in this lecture is pipeline implementation of a processor, the first part. Now, as I have said that we shall be looking at the instruction set architecture of a particular processor which belongs to the RISC category, reduced instruction set architecture. Now, as the name implies, a RISC architecture or a RISC instruction set will consist of fewer number of instructions, simpler instructions and large number of registers, mostly general purpose registers. The result is that it is much easier to implement this kind of processors in hardware. So, this is the reason why we have chosen a RISC architecture as the you can say platform for our example. Okay. So, a few things about the processor. The RISC processor we are looking at is MIPS 32. This is a well known processor, but actually we are not considering the entire instruction set of MIPS 32, but rather a small subset of it, because our objective is to show you how we can implement the processor in Verilog. Let us say we start with 15 instructions, but if I give you 50 instructions following the same principle, you can also implement them. Okay. So, the purpose of taking a small subset is to illustrate how we can design the processor. Fine. So, the important thing to look at before we think about implementation is what are the instruction types and how the instructions are encoded. And after we have seen this, we shall be understanding the different steps of instruction execution, right. So, as I have said, we shall be looking at the pipeline implementation of this particular processor using a small subset of MIPS 32 instruction set, not all the instructions, right. And towards the end, we shall be looking at how we can model this pipeline implementation in Verilog. Okay. Let us have a quick look at MIPS 32, the main features. First thing is that there are 32 general purpose registers. They are called R0 to R31, and each of these registers are of 32 bit in size. Now, we use these registers for temporary storage of data during some computation. Because there are large number of registers, 32, there is lot of flexibility available to the programmer. Okay. And this register R0 is a special register which is assumed to always contain the constant 0, means you cannot write any other value into R0, because in many application you need the number 0. So, you can use R0 for the purpose. There is a program counter which is also a 32-bit register, and a program counter you may be knowing, this is a register which always points to the next instruction in memory which is to be fetched. So, when an instruction is being executed, we have to fetch the instruction from memory, decode the instruction, what kind of instruction it is, and then follow through the steps of execution. And while we are doing this, we will also be incrementing PC to point to the next instruction, so that after our current instruction execution is over, we can go back and fetch the next instruction, right. Okay. Now, in MIPS 32, there are no flag registers as are present in many other processors. Flag registers means 0 flag, carry flag, sign flag, some of you may be aware, and there is a very limited set of addressing modes, register, immediate, register, indexed, and not many more. And another important thing is that the only instructions that can access memory are load and store, and all other instructions, they operate only on the CPU registers. They cannot use any data directly that is stored in memory. You will first have to load that data into a register and then use it in some computation, right. And another assumption we are making, because everything is 32 bits, to make things simple, we are assuming that memory is word addressable, meaning that every word has a unique address and the memory word size is 32 bits. So, the instruction subset that you are considering are summarized. Firstly, there are load and store instructions. So, I am illustrating with examples how they look like. Load instruction is like this: load word LW, and this R2 is a register, R8 is a register, and this 120. This is how we write. The meaning is the value of the R8 register is added to this number we have specified. We call this an offset. We add them up, that is treated as a memory address. From that memory address, we fetch or read the content of the memory location, and the data is loaded into R2. So, the memory is loaded into R2. Similarly, store word. Store word is the reverse. So, means a register R5, its value will be stored in a memory location, where same way the content of the register R25, you add -10 to it, that means -10. These numbers will be represented in 2's complement signed form. This we will see later. Okay. There are some arithmetic and logic instructions which will be considered, these few numbers, where only register operands are used, like add R1, R2, R3. So, here the convention is that the first register is our destination, the other two are the source. So, add R1, R2, R3 means add R2 and R3, store the result in R1. Similarly, add R1, R2, R0 means you add R2 to R0, which always contain 0, and store it in R1. So, you see this is a, you can say, indirect way to move the content of a register into another register. This effectively is copying the value of R2 into R1. Okay. So, when you need to do this, you can use this add instruction with R0. Subtract is similar, subtract R10 and R8, store in R12, and bit by bit and, similar, bit by bit or, multiply R6, R7, store in R5, and this is a special instruction, this is called set less than. Set less than means it checks whether the second operation R11, R12, it is less than or not. If it is less than, then the target register is set to 1, otherwise the target register is set to 0. Okay. These are some of the instructions, and there will be some arithmetic and logic instructions where some offset or an immediate operand is given. Like you have a version of add and subtract instruction, we call them add immediate, subtract immediate. So, how do you use it? Add immediate R1 R2, the last parameter is a number. This means you add the contents of R2 with 25, result stored in R1. Similarly, sub immediate R5 R1 150, so R1 minus 150 stored in R5. Similarly, there is a version of set less than immediate. So, you can write like this R2 R10 and a constant 10. So, here you compare whether R10 is less than 10 or not. If it is true, then the target R2 is set to 1, else R2 is set to 0. There are two types of branch instruction we will be considering, branch equal to 0 and branch not equal to 0. Branch equal to 0 means there is a register specified, we check whether this register is 0 or not. If it is 0, then we jump to loop, otherwise we proceed with the next instruction. Similarly, not equal to 0, if R5 is not equal to 0, then you jump to this level. And there is some unconditional jump instruction j lab, it will always jump, but of course here we shall not be implementing this jump loop. Okay. And the last instruction of our program will be a halt instruction. So, it will stop the instruction execution. Now, it is important to know that how these instructions are actually encoded. That means, in terms of bits, I told that all word size in memory is 32 bits. So, every instruction will also be encoded in 32 bits. So, we will have to know what these 32 bits actually indicate. Okay. So, once you know it, only then you can proceed with the hardware implementation or the Verilog modeling, whatever you say. Okay. So, we need to understand how these instructions are encoded. Broadly speaking, MIPS 32 instructions can be classified into either register type, immediate type and jump type. Of course, we are not considering jump type in our implementation, because in the previous slide we said the J instruction we are not implementing. So, J instruction uses this type, right. So, when you say encoding, as I had said, the 32 bits of the instruction, they will be divided into some fields and each field will be having some fixed widths, and all instructions may not be using all the fields. Let us see that what this means. Let us start with the art type instruction encoding. See, art type instruction encoding is like the add instruction, add R1, R2, R3, like the instruction that I have said, some instructions like this, where there are 3 register operands. So, you add R2 and R3, store the result in R1. This is an example of I type instruction, not I type, art type instruction encoding, register type. Right now, in this type, how we are encoding in 32 bits, you see, the first 6 bits, bit number 26 to 31, this is a 32 bit word, 0 up to 31. This we are calling opcode. This opcode actually tells you what kind of operation this instruction refers to. Because we are considering only a small subset of instructions, 6 bits are sufficient for us. So, in 6 bits actually we can represent 2 to the power 6 or 64 possible instructions, but in our case it is much less. So, 6 bits is more than enough for us. Okay. The next 3 fields, they indicate some registers. In an art type instruction, there will be 2 source register and 1 destination register. The source registers are stored in the first 2 fields, it is called RS and RT. They are stored in bit numbers 21 to 25. So, you recall there are 32 registers, right, R0 to R31. So, to address 32 registers uniquely, you require 5 bits, because 2 to the power 5 is 32. So, in all these register fields you need 5 bits each, okay? 5 bits here, 5 bits here and 5 bits for the destination. So, the bits are given 11 to 15, 16 to 20 and 21 to 25. Now, the last bits, they are used in MIPS 32, but for our implementation we are not using them, because this 5 bits is normally used to specify something called shift amount, and last 6 bits is used to specify some ALU operations, which is sometimes called opcode extension, but these two we are not using here in this implementation. So, let us ignore this, we will be setting all these bits to zeros. Let us take some examples. So, the instructions that we are considering, these instructions can fall in the R type category. They require 3 registers, most of them. Halt does not require any, 0 registers. So, halt we are also putting in this category, because you can fit it in this same thing, because opcode will be halt, other fields will all be blank, they will not be required. And we are assuming that these are the opcodes, all 0 is for add, 1 is for sub, 2 in decimal is AND, 3 for OR, 4 for SLT, 5 for MLT, and all ones. This is actually 30, this is actually 63 in 6 bits. This will represent halt. Now, an example of encoding, let us take a subtract instruction, sub R5, R12, R25. So, subtract the opcode is 00001. So, when you convert it to the instruction format, for subtract we write this 0001, then the 2 source registers R12 and R25. 12 in binary is 01100, this indicates register 12, and 25 is 11001, this indicates register 25, and destination is 5, 0010 is R5, and the last bits we are not using, as I had said, these are blank. So, if you break them up into 4 bits each and write in hexadecimal, this instruction in hexadecimal will be 05992800, right? Fine. Now, let us look at something called I type or immediate type instruction encoding. Let us take an example, what kind of instruction we are talking about. Let us say add immediate. Let us say add immediate, we are saying R1, R2, then a number 50. This 50 is sometimes known as immediate data, that is why we call it immediate mode or I mode. So, there will be 2 registers, the operation and an immediate data. Now, here this immediate data is encoded in 16 bits, right. So, you see, so how the instruction encoding is done here. Again the first 6 bits are for opcode, the next 5 bits are for the source register, like in this case the source register is R2 in the example that we have given, R2 is the source register and R1 is the destination register, right. So, the first field is for the source, the second field is for the destination, because we need only 2 registers, and the last 16 bits is left for the immediate data, 16 bit immediate data. Sometimes this also represents an offset for instructions like branch, this we shall see. Now, the instructions that fall under this I type category are these: load word, load store, they also belong to this category, load, store, add immediate, subtract immediate, set less than immediate, branch not equal to 0 and branch equal to 0, and these are the opcodes that are chosen by us, 6 bits. Okay. Now, some example encoding, take a load instruction. So, I said earlier that a load instruction looks like this. So, R9 is added to 84, that will be our memory address, from there data will be loaded into 20. So, load opcode is this, source is R9 901001, destination is R20, this is 20, and in the 16 bit offset we write 84. 84 is in decimal, if you convert it to binary, this will be the binary equivalent for 84, this you can check. So, again if you convert this into hexadecimal, the hexadecimal form becomes 21340054. This instruction is encoded like this. Let us take another example, branch equal to 0. This I said it checks, there is only one register here, 2 registers are not required, only one. So, if this R25 is 0, then you jump to level, otherwise do not jump. So, here B equals Z, the opcode is this 001110. There is only one source register R25, this is 25, but destination register in this instruction is unused, we leave it as all zeros. And then this 16 bit is the offset. So, here we are writing it at YYY, this can be anything in fact. So, the place where you want to jump we will be specifying some offset here. So, what will happen is that this offset value will be added to the contents of the program counter, and that way the address of the next instruction will be calculated. This is how branch will take place, right. And again this number if you convert to hexadecimal, it will be 3B20, the last y's I write it YYYY, okay. This is 3B, 2 and 0, fine. And the J type instruction that I had said that we are not implementing this, but actually J type instruction looks like this. It consists of an opcode and a 26 bit immediate data. This is only for the jump instructions. So, here we have also assigned a opcode, but in the implementation we will not be using this. This is not implemented. So, a quick view of the 3 instruction encoding types. So, one thing you see, you forget J type because we are not implementing this, we are not looking at J type. But among the R type and I type, one thing is very clear, you see the first 6 bits are opcodes, the next 6 bit is always the source, the next 6 bit is sometimes a source, sometimes the target destination, and for R type the next 6 bits is the destination. So, what we are saying is that we really do not know what type of instruction this is unless we decode the instruction. But the strategy that we will be following is as follows. To speed up things, we will be assuming that there are 2 source registers. We will be taking the 2 source register numbers, there will be a register bank, we will be prefetching 2 registers for those register numbers. We do not know whether they are actually required or not. This will come to know later only after decoding. But in case they are required, the registers can be fetched and they will already be available with us. This way time is saved, right. So, now what we are saying is that I have just summarized it here. Some instructions require 2 registers operands RS and RT like add, subtract, while some require only RS like add immediate, subtract immediate. But only after decoding is completed, that means when you decode the opcode you will come to know exactly what kind of instruction is this. So, what I have just now said is that while this process of decoding is going on, you prefetch the registers assuming that these are, it is an R type instruction, assuming that you need both the registers. So, register numbers are already there, you access the register bank and prefetch them. But if later on you find that it is an I type instruction, then the second register that you have fetched, you will simply ignore it, only the first one will be used. This may or may not be used later. Similarly, for the immediate data, for I type there can be 16 bit, well J type we have not implemented, for J type it will be 26 bits. So, we do something called sign extension, we will talk about it later. We convert it into a 32 bit number and get ready, so that later on when you need it, already the value is available in 32 bits. So, the addressing modes that are available in MIPS 32, this is very quickly summarized here. Register addressing, an example is this, where all the operands are stored in registers R1, R2 and R3, the destination in R1. Then immediate addressing, one of the operand is an immediate data 200. Base addressing, there is a register, there is a number, you are adding this number to the register to get the effective address or the operand address, this is base addressing. PC relative addressing, branch. So, whatever offset is specified here, that is added to the program counter to get the actual address of branch. and jump of course we are not considering, it is very similar. This 26 with offset will be added to PC. So, with this we come to the end of this lecture, where we gave you an overview of the processor that you are trying to design. Just one thing you remember, some of you may or may not be having proper background in computer architecture and organization. For those of you who have already done a course on computer architecture or organization, you will be understanding much clearly what I am talking about. I am talking about a processor, I am talking about instructions, decoding, steps of execution and so on. But if you are a designer wanting or trying to learn the language Verilog, you just stay with me. You need not understand all the things that I am talking about, but ultimately you try to understand what is the problem that you are trying to model and how we are modeling in Verilog, you are implementing it in pipeline and what is the process involved. In the next lecture, we shall be continuing from here, we shall be talking in more detail about the steps of instruction execution and how we can design the, you can say controller, you can say how the instruction execution is done inside. Okay? Thank you.